homework. And these two objects contain the data I use in this homework, and the fish and the density of fish and copepod. And first, I want to calculate the beta 1 from original data using this formula. And first, I make a matrix to calculate it. And this two of the matrix. And I write the code to using this formula to calculate it, and finally I guess the beta 1 is 0.116. And then it's the permutation step. First, I use the for loop to run the permutation, and I run randomization is 5,000 times. And first, I use the run if function to generate a random organization of the number between 1 and 34. And I rank it so I can get the number 1 to number 34 in randomization or arrangement order. And I can use this row of number to generate to shuffle the density of the fish, so I can get a randomized dependent variable. And the copepod density is just as the same. And so I also can get the beta 1 for each permutation. And to visualize the distribution of the permutation, I use the ggplot function. And the three main functions I use there are geohistogram to make a density histogram, and geodensity to make a smooth density line. And also use the geo B line to create a vertical line and check the position of the original data, beta 1. And the result is like this. You can see the histogram of the density, and also the density line of the permuted beta 1. And the red line is the original beta 1, and so we can see they are situated on extreme two sides of the distribution. And finally, I calculate the p-value, and the definition of the p-value is the proportion of distribution higher than original value. And so I use this code to calculate the p-value. And because it is two-tailed, so I consider the positive value and the negative value. And so I use the ABS to get the absolute value of the each beta 1 in each permutation, and divide it and see how many value higher than the original beta 1, and to get sum length and divide it by 5,000, and the result p-value is 0. I get is 0. So I can conclude that beta 1 is significantly different from mu. And question two asks us to use the randomization test to test whether significant difference exists between the density of these two species of copepod. And also I import the data sets just like previous work. And or I use the use which function to find the row which rows name include the character of the species name, these two species name. So I can these two objects contain the the density of the two species. And first, I want to calculate the difference between mean density from original data. And so I first use mean function to get the mean density of each copepod, and use minus to to get the difference between them. And finally, I guess the value is 69.66. And also do a permutation. And difference from previous work from question 1. In this question 2, is required to put the two the density of the two copepod into a pool, into a same pool. And also I use a for loop to generate a random to generate a permutation 5,000 times. And also I use the round if function and rect length to get the random order of the numbers. And to arrange these two species, the density of these two species, I make a matrix to contain a shuffled pool, the density after shuffling, and this matrix contain the two pool value, two shuffled, the density of the two copepod after shuffling. And also I create a vector to contain the difference of mean between the two species. And also I use the ggplot to make a plot. Also the histogram density and V line. I guess these plots, and we can see that the position of the positive and negative value is is closer to the center of the distribution. And finally, I get a p-value from the similar code. So we can get I guess the p-value is 0.25. So I conclude that there is no significant difference between the density of the two species. And it is my end of my presentation. Thank you.
Very good. Any questions? No? Okay, let me go to the next one before I explain a bit more on the integration. Okay. Break up. Okay.
Okay, everyone. My name is Chen Chen from ILNTU. And first, we are calculating the beta 1 by permutation and 5,000 times. So our hypothesis is beta 1 equal to 0, which means that it's just beta 1 is random, and our alternative hypothesis is beta 1 not equal to 0. So first I read the data. And second, I try to calculate the beta 1. Beta 1 is 0.11. And then I randomize 5,000 times. So first I just create a matrix and use the apply function. And here I shuffling the fish. So I got the order of here, so I can shuffle the fish. And then I calculate each of the beta 1 5,000 times. And to calculate the p-value, so here I have the result we just permutation. I use the absolute result, which we use the two-tail test, and just bigger than the original data, so we can see it is a p-value, and our result is almost 0. So it's very significant. Beta 1 is significant different from the generalization. So we reject the new hypothesis. And here's the plot. The line is the original data in two-tail. And here's the plot code. And second, we want to know about the two species where they have different each other. So here's our new hypothesis that the first species mean minus the second species mean is 0. Means that they are randomized, they don't have they are not significant. That means that the mean of each other is same. And the second, the alternative hypothesis that the first species and second species are not the same. So first, I read the data and use the diagonals, matrix to calculate the density. So it will be fast more. And I have these two species density, so I just mean and minus together to get 69. And then I do the randomization about O, B, and CP to put together. I also have order, then a shuffle it. So here's the shuffle. And then I minus each two part of mean. So I just take the first 1 to 17 as the first part, and the second part is 18 to 34, and the second part, so I just minus together.
Why 17? I think it should be 34 and 68. Because that total is the inverse station. Your code is correct, but it should be
60.
Should be 34 and then 37 to 68. Your code is correct. 我就是说那个应该分成两半的话，总共34加34是68，所以应该是1到34，然后减掉那个35到65，但是扣是对的。
And also calculate the p-value, and is 0.244. It's not significant, so you accept the new hypothesis. So these two species are not significant difference. Here's the things.
Okay, very good. basically the same. The same way of doing the calculation. Any question? Easy. Okay. Thank you.
Yeah, I have a final minor comment. Yeah, I have a final minor comment uh, on this p-value calculation. So, mathematically, it's impossible to have p-value equal to 0. Mathematically, it's impossible to have p-value equal to 0. They must be smaller than something. So usually, it's a convention that we will take the small. If you after calculation you find out the p-value is 0, then you should report the p-value is smaller than 1 of a number of permutation. Okay, so in this homework it should be 1 divided by 5,000. Okay, the smallest p-value you can get, right? And if you are not happy with this number, you may try to increase the number of permutation. If you increase the number like say 10,000, right? And if this is 10,000, right? Then you should report p-value. If after computation your p-value is 0, then you should report p-value smaller, not 0. Like point or 1, right? Right? You should always report like that. You shouldn't report the p equal to 0. This is wrong. Because the statistical sense is impossible to have p value equal to 0. If you just continue to increase, then eventually there will be this very minor possibility that p value is a very small. The other one. So we don't report p value equal to 0. We have to report the p value smallest to the possible p value according to the number of the violation. Is it okay? Right, so this is a convention, okay? So any question on homework? No? Right, so it should be, yeah, I'm sure that you're now already familiar with this kind of remarriage approach or bootstrap, so you should be able to write your code. Okay, then I'll start the lecture for today. Okay. Today we will change completely the topic to the minimization issue. That very good reference is the numerical recipe chapter 10. Minimization question actually generally can be considered as optimization questions. 最佳化问题 okay, optimization questions. Right. Simple is a question that we learn, or at least I learned from high school, is how to solve the root. 怎么样解到一个方程式的解 ？Okay, how to solve the root? So you need to find x such that f of x equal to 0. Right? So this is a solution. So this is the most fundamental minimization questions, or we call it root findings. The very famous method is called Newton-Raphson method invented by, of course, by Newton. These methods are mathematically very simple. We can consider that fundamental definition of a derivative. Okay, f prime at xi is equal to this formula. Okay, so this is the definition of a derivative. If that the difference between xi and xi plus 1 is very small. Okay, take it to the limit, right? And then according to this formula, we can derive this. We can move this side, move this that side, so you can find the very simple relationship between the iteration of xi plus 1 versus xi and this relationship between f of x and f prime of x. Right, so this is the fundamental rule of calculus, which eventually needed, right? Okay. So suppose we have an equation, f of x, and then we are able to calculate the f prime. So we need to be able to calculate f prime. There's certainly some condition that we are not able to calculate f prime. In such case, this method cannot work, right? So we need to require that f prime can be analytically calculated, right? So you already have a prime for fx. You can just initially choose some random initial condition of x1, right? xi, so x1 and 2 and 3 and so on, right? So initially you just choose some random number as the initial condition, and that will iteratively do the calculation. And eventually we will find that f of xi equal to 0, very close to 0, perhaps not 100% correct, exactly equal to 0, but it is close to 0 enough. So you can define some kind of improvement stopping rule. So we can calculate the improvement, okay, the difference between xi plus 1 versus xi, and divide by xi. So how much improvement you can get for each iteration. If the improvement become very small, then it will stop. Okay, stop. You set tolerance larger than improvement. If you reach some kind of threshold, then you stop the iteration. So usually we may say we can make that tolerance, we may say set to 10 to the minus power 10, right, or 10 to the minus power 8, very small number. That means that the improvement is very, very small, no longer change. Then we claim that we already find the root. Okay. So from a figure, you can see what this Newton-Raphson method is doing. So it is the initial random starting point. It can be anywhere. It can be anywhere on this line, on this real line x. Then what it's doing is that the calculate tangent map this and calculate tangent map. Right. So in this very simple case, it quickly reach that find the x where f of x equal to 0. That's very, very fast to find. Okay. So this is an ideal case. If you can start here, you can start it from this side also. But if you start from this side, you shoot here and then comes back again, quickly reach that convergent solution. If that f of x is very simple, right? So you can find that root quickly using the Newton-Raphson algorithm. And it's very easy to write your code to do this Newton-Raphson algorithm. First, you just need to follow in this relationship, and then you need to, of course, first calculate the analytically solution for f prime. Okay, the equation. So there are some cases that Newton-Raphson method does not work. It's called pattern of divergence. So if f of x is complicated, right? And then by chance, you might encounter this situation. So the first tangent comes here, and then for the next iteration, the tangent you cannot find. Right? The tangent is horizontal, and then you cannot find that the tangent intersects with this line, and therefore it's divergent. So then that calculation brought up. You cannot find the root under this kind of condition. So we need a different way to find the root okay, or at least to minimize some kind of solution, find a minimization of some kind of solution. So that's the basic concept of minimization. Here, yeah, the minimization is 0, right? Minimum value is 0. It's the most intuitive minimization question. But certainly there are some other condition that the minimization is not 0, but we just want to find something that has to be minimized. Okay. The most encountered scientific question is to find the best fit of your line, best fit of your line. So in this example, the red dot data, we do an experiment, we can obtain the data. The data, very simple, is a concentration of your substrate, and the reaction rate is some kind of chemical reaction. Then you increase the concentration of your chemical, and that's the reaction rate. Right? So there's an increasing relationship between the chemical concentration and the reaction rate. However, that relationship is not linear, it's saturating, because we all understand that if we increase the concentration, the increase in the reaction rate, but if we continue to increase the saturation rate, it's going to be limited by some other chemical concentrations. Right? So it's going to saturate, something like that. Right? This relationship, this blue line, this kind of relationship can be written as this kind of equation. So rate following this relationship, S is the concentration of chemical, Y is your rate. Then Km and Vmax are some kind of parameters you have to find that decide that blue line. Vmax is the maxima rate, it is maxima. Okay, eventually you reach some kind of maxima. Now it looks like a maxima, but actually it continues to increase a little bit. So you have to fit on this maxima. And Km is called half saturation constant. Km is that reaction rate about half, but what is the S? Okay, so this is some kind of parameters, right? So of course there are some very important chemical meaning of these equations. However, right now we don't need to worry about it. We just need to understand that we need to find these two parameters, right? So basically we need to find this blue line, okay? And that blue line will be maximally go through all the data points, right? But of course it cannot go through all data points because there is some measurement error. So you want to find the best fit of your blue line, the best fit your data points. So that's the scientific question. And then we already know a priori that equation can be described as this equation. Okay, this line can be described as this equation. But we already know, so this is according to the textbook, we know this line can be described as this equation. And then our task is to find Km and Vmax. Right? If you find a Km and Vmax, then you can have this blue line. Is it okay? So that's a question. So how can you find your best line, best fit line? Okay. In a very simple example, we talk about regression, right? But we know the regression line there's an analytical solution for the slope. But in fact, if you don't know the analytical solution, so this is some kind of regression question. Also, this is a linear regression, and we know this line, right? We know this is y equal to alpha plus beta x. But similar, we have two parameters, alpha and beta, and then we're going to find this line that best fits that equation, right? And then we know there's errors. So these are errors. We'll call it residual, right? So here, similarly, we have error, right? So that again, that's a residual. So we have very different residual, right? And then we can calculate the sum of square of error, right? Remember your regression. some of the square errors, right? And we're not going to minimize this. Right? Minimize this. Right? So if we minimize this, we find this red line. And we already know that red line. I already showed you the formula how to find the red line. Right? In fact, when we find the red line, we are find that solution minimize the sum square error. But here is more complicated. Here we have a nonlinear. We have a nonlinear curve. We have a nonlinear curve. We have a nonlinear curve. So the x, in this case x, in this case s appear here and here, right? So we cannot solve analytically. There's no mathematical solution for beta. You cannot use that linear algebra to solve the beta because now the equation have a nonlinear form, so it's impossible to solve that equation. Okay, it's impossible to solve. So we need to numerically solve. We need to find the V max and Kn such that the sum of square is minimum. Okay, the minimum. So it is called a nonlinear least square estimation. Okay, least square means that we make that square of error least. It cannot be zero, but possibly make it very small. The smallest as you can, right? So it's the least square estimation. Okay, and then from statistical sense is a least square estimation, right? And from mathematical sense is that we're going to find that blue line that fits the data. And that blue line is already a formula we have learned. We already know. We have decided before the calculation. We already believe this is the equation. Okay. Okay, I'm going to. So the agenda today is going to introduce a few approach to do the mineralization question, to deal with the mineralization question, and I'd like to explain some. There are several ways. Some are very fast, okay, and some are slow. But the first one usually have a difficulty to reach converge because all these for all these approach you have to calculate x plus si plus 1 versus xi, right? So it's going to make an improvement. Sometimes the fast method they changed a lot. So the difference between xi, x plus or I plus 1 is large. So they're jumping around. So cannot reach the convergence. Okay? But some approach convergence is very slow. Okay? And the second issue is that fast method usually require calculate derivative. Okay, f prime. Okay, usually we have to calculate f prime. Take advantage of f prime to do the mineralization procedures I will explain later. Right, this is related to Newton's idea. There are some other methods that does not require calculate f prime, but all usually those methods do not require f prime computational intensive, much slower in terms of computation. All right. So I'm going to introduce the more detail is Newton's method, okay, and some other non-parametric methods. Right? And there's something in between I'll quickly go through, but without very detailed explanation. Okay, that's the agenda today, and then we'll go on. All right. So this is called Newton's method for mineralization question. This is probably the most powerful approach to do the mineralization issue for a question that where the derivative can be calculated, and the curve is not so strange. FLS is not so strange. So again, delta x is a very small perturbation deviation from the x, and then we will take a Taylor expansion. Okay, remember I talked about Taylor expansion many times. So for any x, we can write the Taylor expansion like that, right? So we can write the f of x, f prime delta x, f double prime delta x squared, and so on and so forth, right? So in this case, we are going to keep the first two order term and ignore higher order, right? Assuming the delta x is small, okay. So we can then take the derivative, we take the derivative of this equation. So this is f of x, this is constant because this does not depend on delta x, right? So this disappear, and this become f prime of x, and this become f double prime delta x. But then we make the derivative and make it to 0, and then just solve for the schema, right? I don't know whether you learned in high school. If you have an equation, we take a derivative with respect to x, and then make it to 0, then solve for the schema. 极值的计算就是对于那个参数对于那个 x 做微分嘛，让它等于零，就得到极值。So the schema may be maxima or minima, but anyway, when you find the schema, and then we can decide the minimum. Okay. So that idea is that we are going to take advantage of Taylor expansion and take a derivative with respect to delta x, and then to solve for the schema. So to solve the schema is that you make that equation equal to 0, right? Make the equation equal to 0. All right, and then after some linear algebra, so delta x is xn plus 1 minus xn, right? So you can do some manipulation, become this. So it's okay. You can do some linear algebra. Here, usually we write like f prime as a delta. I'm not delta. I don't know how to pronounce this. So usually mathematically is a gradient. Okay, so this is gradient. This is f prime. And double prime, we call it Hessian. Okay, we call it Hessian. And then we have to take inverse because it is in the denominator. It's the inverse. So this is a Hessian by definition, but I just give you a name. Okay. So if you can find the gradient, okay, if you can find the first derivative, and you can find the second derivative, and you are able to use this formula and give initial condition and you do the iteration. Right? Keep in mind, this is always known. This is always known because in this question we assume f prime is available. Right? We assume f prime is available. Okay? If f prime is not available, we cannot use this approach. We assume f prime is available, and you know f of x, and you can calculate. You can always calculate f prime, right? And then we can know whether it's available or not. Right? So this is very simple. And then f double prime, we can estimate it, numerical estimate f double prime using f prime. Okay, we can approximate we can approximate the double prime from single prime that I will explain later on. So you don't need to worry about double prime because it can be estimated, approximated using first derivative. So because this always exists, and xn is some kind of value you're going to put in, right? So this is always available. It's okay? So we don't approximate this because this is always available. So given initial condition, you put the S1 in, and S1, 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 right? So everything is available, calculable. So you can always get S2, right? So it's iteratively. So give it initially, choose and randomly some initial condition. Okay? And then you put in this function, and then you can always evaluate. It's okay? Any question? Okay, well not this you don't have to estimate this because this can be calculated, it's available, always available. So there's no estimation procedure here. Just put in the number and then do the calculation and iteratively. Okay? So you need to initially get some random initial condition. So usually you multiply this equation by a being a small number, a. So a is between 0 and 1. Okay, so without putting a, of course, a automatically is 1, right? But the idea is that we don't want to change the delta x. We like the delta x to be small. We like delta x to be small, otherwise it's jumping too fast. So we put the small number. It's obviously chosen maybe 0.01, 0.1, depending on the question, research question, depending on how complicated the equation is. If the equation is very complicated, it's better to have a small a, right? Otherwise, 0.1, 0.01 is okay. So this is just to stabilize that iteration procedure. Otherwise, the data is too large, jumping around. Okay. So it's better to give an example. Just use that equation. Use that equation. So again, we can always, if you find, I call this beta 1, I call this beta 2, right? And then if I assume I already find a beta 1 and beta 2, of course we have not found, right? But assume we can find a beta 1 and beta 2. And given any x, you can find y, right? So y is the output of this, you can get a y. The difference between your yi and yi hat is a residual, right? So this is a residual. It's okay? You have a hat residual. So so sum of squared residual is sum of squared I squared and something. And here I make I to 7 because in this equation I have 7 i's. Okay, just to tie this to that example we had. I call it the function phi beta. So what we really want to do is we want to minimize, find the beta. We want to find beta 1 and beta to minimize this, right? So that's our agenda, okay? And from Newton's method, so that's the iterative equation, that's the algorithm, so beta n plus 1, beta n plus delta. So beta, remember here, beta is a vector, beta has 2 elements, right? So in reality, there is no limitation of the number of beta mathematically, but if there are too many beta, of course, the computation become more complicated in terms of convergence. But the computation does not change much. The computation is always the same. Here, just remind again. So we should follow this equation, right? We must follow this equation. So what is delta? Delta satisfies this equation. Okay, so idea is this one: beta n plus 1 equal to beta n minus Hessian inverse gradient, right? So not this. Okay, I didn't include A, right, to avoid this explain of mathematics, we don't need A. Okay, so H is Hessian, G is gradient. So we need to find G and need to find H, right, before we put it this. So what is G? So I have I from 1 equal to m is 7, okay? I 1 to 7, all right? And the G make a derivative with respect to beta J, okay? With beta J, beta have 2 beta, and anyway, I write it as beta J. So if you take this function, and take the derivative, right? If you take this derivative of 2 outside the beta J, right? Is okay? Take a derivative of this. Okay, that's a typical mistake. We are going to minimize the sum of square error. We are not going to minimize that equation, okay? That's a typical mistake. When you write a code, we are going to minimize this. We're not going to minimize this, okay? Because we minimize the sum of square error. We don't want to minimize the residual, right? We have to minimize the sum of square error residual instead of minimizing the residual. Everybody understands the reason, right? So this is the basically mathematical things because I can be positive, negative, and then cancel out, right? So you have to minimize the sum of square. That is a basic approach. All right, so you get G, you get G, right? You get gradient, right? And keep in mind, I have 2 beta, but anyway, we can write this way, right? But in reality, you have to write this as a matrix because I have 2 beta. Right? And then the second derivative, we take a G and take a derivative again, right? So this Ri, so this is chain rule, right? So the Ri take a derivative, 2 outside, Ri take a derivative, the Ri d beta J, but then the Ri d beta K, right? again, I have two beta, beta j and beta k, right? So this term, this one. And plus, I take this derivative, I'm sorry, I keep this, I take derivative here and then keep this term. And then I keep this term, I take a double derivative of this one. Okay? So that's the chain rule. Like a chain rule for a second derivative. Right? So I'm sure you understand this. Alright, so because we are going to simplify this equation, we're going to ignore the second order derivative. So this is okay, take derivative twice. Okay. And then we can ignore this because in any case we're going to do some approximation iteratively. Right? So even without this, that just take more time, but the computation is easier. Right? So we can ignore this without any loss. Right? So in fact, the Hessian become Jij and Jik. Okay? So we can approximate the Hessian using two Jacobian. Okay, using two Jacobian. So these are the entries of Jacobian J. Right? So we can then rewrite that equation as this G is this, H is this. That's how we can end up with this equation. Okay? So keep in mind that in reality we're going to write that J in the Jacobian in the matrix formula. Okay, matrix formula. So there'll be 2 by 7. The matrix will be 2 by 7 because we have 7 elements and 2 beta. Okay? So for the example, so that is I, we have to minimize some square and then you can calculate your J. So the Ri, the beta 1 is like that. The Ri, the beta 2 is like that. It's not so difficult. You can just take the square of this and then do the calculation, right? Okay, so this is not so difficult. You can, but certainly for the Newton-Raphson method, the most first step is you need to be able to calculate this, right? Otherwise it does not work. Right? You have to calculate derivative. So there's a derivative and a derivative. So you basically take this and calculate derivative. Right? So that's the simple form, but I have I. What is I? I is just the 7 numbers, right? 7 numbers. Okay, so you actually have all the xi. You have all the xi. You have all the xi, right? Because all the xi are here. All the xi are here. So you have 7 xi. All right. So J is a 7 by 2 matrix. So you can write this in the matrix form. You can write a computation of this in the matrix form. So beta is a beta 1, beta 2. So this is a vector. This is a vector. And this is a this is 7. This is the price of 2 by 7 and 7 by 2. And then so you have to do the inverse here. Right. So that's so if it's after the calculation. So Ri also Ri is 7 by 1. So everything that after do the calculation, the dimension is matched up. Okay, dimension is matched up. Okay, so this is the matrix formula. The dimension will match up. Okay, so this become a vector. So after calculation, delta become a vector. Have only 2 elements. Okay. So in terms of computation, you can imagine that computation is super fast because everything you need to do is matrix operation. Okay, matrix operation become very fast. But you don't really need to calculate each element by element and do the sum of square. That's all very complicated, tedious computation. In reality, very fast. Okay, with a matrix operation. So the procedure is very simple. So you have to do some initial guess for beta. Okay, and then you calculate data using this formula. You calculate data by using this formula. And now everything is available because the derivative is available, right? And then Ri is also available, so everything is available. And you just need to plug in the number. Just need to plug in the number. Okay, and then you adjust. We make a small a and repeat it until convergence, until g is approximately 0. Okay, delta, because the delta is the difference, right? Delta, so the improvement become very, very small, then you stop. Right? Which means the delta become very, very small. Until delta very, very small, then you can stop. You can say how small is small. You can again set up some kind of tolerance, stopping rule, and then we're going to stop. It's okay? The Newton-Raphson method, this is one of the most efficient way to solve the minorization questions. Okay, it takes advantage of Jacobian and take advantage of Hessian. Okay, so very fast to converge in ideal condition. Very fast to find a solution. All right. And with this, this is probably the most. This is a concept involved the first derivative and second derivative. Okay, so maybe complicated enough and fast enough. So an alternative approach, which is slower, alternative approach that is slower, called a gradient descent approach. In this approach, very simple. Again, that's the rule. So A is some kind of constant, right? Delta is improvement through time, and then here, delta is used to help the improvement. So how do you decide delta? In the Newton-Raphson method, we find that delta is slightly complicated depending on first and second derivative. In this gradient descent approach, we are only taking the gradient is your delta. In the example, we have two delta and we have only two elements. It's very easy. We just need to calculate the derivative. Okay, we only consider the derivative. And that derivative tell you what? Tell you the direction and then the slope, the moving toward the solution. The idea is like that. So this is suppose this is some kind of landscape of the arrow turn depending on the beta. Okay, depending on beta. So this is destiny. This is the final solution we have. Right? We don't know, but now we get some initial condition as 0. We're going to find that x. Right? We're going to move it toward x. So if you use that gradient descent, or so here this method, gradient descent approach. Okay, you can imagine. Ideally, we'll calculate derivative. We'll calculate tangent of this landscape, right? Because this is minimization question. So this is a low value and outside large number, right? It's a value. It's okay. It's a value going to work, right? So the gradient tell you the direction to move toward the center of the value, right? Because you here calculate gradient going like that and going continuously forward, right? So without any mathematics, with the minimum mathematics requirement, we are always able to find that tangent in that space and then move toward that space, move toward the lowest value along that tangent, right? So without any mathematical assumption and anything, we just need to follow that tangent. Eventually, we're going to that solution. It's okay? So that's the green method, that's the gradient descent. Only require Jacobian. And what Newton-Raphson is doing, what Newton method is doing, what Newton method is that use the curvature information to take a moderate route. It's going to shoot like that. Okay? Because Newton's method calculates not only a gradient, but also the Hessian. Right? So when Newton method is going to evaluate both the gradient and Hessian. So it needs to know where to go. But the gradient method is very slow. You always find the deepest, the largest, the largest magnitude of your gradient. So is that going to take a long one, okay, take a detour. But this one actually take advantage of the curvature, the double derivative. First derivative is tangent, right? Slope. The second derivative is the curvature. Take advantage of curvature. So it knows where to go very faster to find a solution. So geometrical interpretation, the difference between gradient descent versus Newton's method. Okay, so that's why Newton's method always faster because Newton's method take advantage of the second derivative and find that moderate route to the solution. But gradient descent, you have to always move around, always find, continue to find. Okay, the deepest gradient. Okay. So the problem of the Newton's method is sometimes the failure to converge because you jump too fast. Okay, jump too fast. The state move too fast, so it's difficult to converge. And the gradient descent is very slow. Okay, it's very slow. Okay. So there are some LM algorithms. The LM algorithms modify that equation. Instead of without this term is Newton's method, right? But now we include this term to improve the convergence. Okay, so mathematically speaking, that algorithm is a linear interpolation between the result of the gradient and Gauss-Newton's method. Okay, but I'm not going to explain how we derive the lambda and d. Okay, so I already explained this. So steady descent typically follow an inefficient zigzag path to the minimum of the function. They're going to up and down. It's very slow. Okay. Another way is to fit a quadratic curve to the steady descent. So instead of that move like that, we have to fit the height so it go faster. Okay. So the method is called the conjugate gradient descent. If you're interested, you can read the detail of that chapter. I'm not going to talk about that. It's too much mathematics. All right. Any questions so far? For that method depending on derivative. No? Okay. Before I move on to a complete different non-parametric method, we'll take a 20 minutes break. We'll come back at 10:35, and I'll talk about different methods. And you can think about that. The way to do the program is just calculate the Jacobian. Okay. Or I'll continue. In 30 minutes, I'm going to finish the lecture for today. Now I'm going to talk about a more general approach, but that approach is very slow. This approach is called a simplex method, and this approach does not require calculation of a derivative, and therefore is general. But as I will explain, is a sort of searching minima point algorithm is very slow and require a lot of computation. First, let me explain what is simplex. Simplex is the minima polygon, okay, a minima polygon, and we have something in between, inside. So we're going to decide a simplex, okay. So I'm going to use that example. Use this two-dimensional case as an example. So we have beta 1, beta 2 only. We don't have beta 3, two-dimensional simplified case as an illustration. But you can imagine mathematically, this can be generalized into any dimension. Okay, the calculation, the idea, or the mathematics are all the same. So in a two-dimensional example, if we decide a triangle, we can always have some point inside that triangle. Okay, so ideally, we have maybe some solution here, some solution here. We don't know, but then we're going to decide some kind of triangle and move that triangle around, eventually find that solution inside that triangle and then shrink the triangle until you find a solution. So that's the idea. Okay. So in a two-dimensional case, so initially we need to decide 3 points. Of course, if we have a three-dimensional case, we will decide 4 points and so on and so forth, right? Because we need to decide. Eventually, we seek for that simplex that has that solution inside. Okay, inside. So it is a very simple case. Okay, so we initially randomly decide some kind of guess beta. Okay, some initial condition. Randomly decide. And then we're going to create a triangle around that initial condition. Okay, beta 1, 0, beta 2, 0, right? So that's the initial condition, purely randomly chosen. Okay, and then we can always decide some kind of random arbitrary triangle had that initial condition decide. Okay, true solution may be here, but doesn't matter, we always decide some kind of triangle. Okay? And then with this triangle, we can make some kind of evaluation, some kind of evaluation of f of x. Because once you decide that initial condition, you decide these 3 points. You decide that 3 points. And then with these 3 points, we can always evaluate f of beta, right? F of beta. So we evaluate this and evaluate this and evaluate that. And then you can always find some kind of number, some kind of value. Again, that's a minimization question, right? So low is good, high is not good, right? Low is good, high is not good. So which means that solution is more close to this side and not this side, right? Because this is the lower value. So it's a minimization question, right? So it's lower is good. But in any case, given this some initial condition, you can always evaluate your f of beta, right? Or more generally, I just call it f of x to be simple like that. Okay, so initial at the beginning step, you can evaluate that 3 points, right? So you always have low, high, intermediate, right? In any case, you can rank them, right? You can always rank them, right? And then how this triangle is to move? You can move this way, or move this way, or construct and so on. There are various ways to make movement. But does not want to move this way, right? Because this is high. It does not want to move, it want to move this way, or even beyond. So beyond or construct, whatever. So anyway, solution is here or somewhere in this domain, right? Not this domain. Okay. So the simplex method is going to move the triangle around that space and find that solution. So that's a lot of decision making. The decision making depends on your f of x, depending on your evaluation of your f function. But you no longer need f prime, because we only need to evaluate f of x, f of beta, maybe I should just say f of beta parameter. Okay? So again, so that's the initial condition. I have m1 is the lowest f. I have n plus 1, so the highest f, and the intermediate, or I call it second highest f. Okay, you can make an evaluation, and then we also need to decide along this plane, along this line, right? If it's three-dimensional, this is a plane. We can then need to decide the refracted height. The reason we want refracted height because we don't want that, right? This is high, so this is the second highest, it's the lowest, right? We don't want that, so we want to go this way, so I calculate refracted height, I. So this is always doable, right? So mathematically, it's always doable. And then we can evaluate this point, f of this point, right? So then we evaluate this point, and then if we find this is smaller than that, this is lower than the lowest case. This is lowest. So this is even lower. If this is even lower, the solution will be somewhere here, right? Solution is impossible to be here, right? Somewhere here or somewhere here. But if this is lowest than this, of course, you may imagine solution somewhere on that direction, right? So if the condition like that, then we make a guess that's extrapolated IH. Okay, extrapolated IH. Okay, so usually you can arbitrarily make it maybe 2 or 3 times of this distance. So make it 2 or 3 times this arbitrary. Okay, anyway, we're going to search, right? So this is arbitrary, to make it that extrapolated IH. Okay, so and now your choice after you do this, your choice will reorder them, right? And then the lowest will be a minima of this or that, right? And then you keep this one, right? And you got to decide to keep this or keep this, right? Because that's your guess of your next step. So if this condition is true, okay. Second possibility, if this one is larger than this one. So this one even larger than that. This is definitely not good to go that direction, right? So this is already highest. Now it's even larger than highest. So which means the solution is somewhere around here. So this is a lucky case because we can shrink. Usually cut into half. Which means the initial case is very good. That solution is very likely to be here, right? Okay, we cut it in half and reorder. Okay, reorder that 3 points. So this is a fortunate case, right? So if under this condition, this is a smaller than that one, but the larger than that one, right? So this is that direction is good. However, this is larger than that, which means it's impossible to be that direction. Impossible to be beyond, right? So we have to make a constructed IH. So usually again we cut it into half, like we decide that, and then we link. We have to decide which one we like. Okay. All right. And final case, if this is the condition, then this is good. Then we again relink. So this exhausts all the possibility. Okay. So the search have if else then if else then excuse me. So there's only 4, so it's the initial condition, there's only 4 possibilities. There are totally only 4 possibilities. okay, to decide how to move for the next step. Right? So every step we're going to decide which move we need, right? And then we decide a triangle, and then again. Eventually, that triangle is going to become smaller and smaller and smaller and smaller and smaller, and then we find until the improvement is very small, and then we have stopping rule, and we stop the estimation of your beta. Okay, so it's based more or less like exhaustive search on that parameter space. Okay, and move around and do the exhaustive search. Eventually, you always find a solution. Okay, the ideal case, in a very simple case, a single value, right? If there are many values, of course, this becomes complicated. You can check in the local minima. However, assuming that it's a very simple case, then you can find a solution. Take a long time, actually, take a long time. Take a long time, but eventually find a solution. Okay, find your minimization solution. So the syntax, the minima context whole include something inside called syntax. The syntax move on the topography defined by function. Okay, the extending and constructing the pseudopod, bar. Okay. So advantage is and then so as I said, they may be checked by local minima. If you move and then but that's not global minima. So what you really need to do is you try different initial conditions. You can randomly starting from different points. And then eventually find the minima, right? Or there may be some, in a very simple two-dimensional case, you can try initial condition, many combinations of initial condition. Because with the beta may be some biologically reasonable parameters, so you can constrain that space, so you can try different combinations. Try all the combinations, all the potential. Of course, it's impossible to try all combinations, but reasonable combinations, and then you can find minima. Okay, so that's the solution. Okay, and that does not require duty. Okay, and that requires a lot of computation. Okay, require a lot of computation. The evaluation of f of x for all the triangles move around, so a lot of computation. So this is usually very slow, right? So if we have a beta 1, 2, 3, or many beta, it's become computational very intensive to try high dimensional or possible cases of that syntax. Okay. And today we talk about a very basic concept of optimization solution, like a gradient descent, Newton-Raphson syntax. That's almost like the most easiest and basic way to solve that optimization problem. And then if you encounter a very complicated optimization question, then you can like simulate an annealing genetic algorithm and so on and so forth. But I'm not expert on this topic, and then I'm sure in the engineering department there's like whole year class about optimization questions. So you will take a more advanced optimization class that teach the more advanced approach to do the algorithm with more advanced optimization approach. Okay, it's okay so far. We have parametric and non-parametric approach to do the minimization. And then you might ask, how about maximization? There's no maximization question, because we can always take a negative sign in front of any maximization question and make it minimization question. It's okay? So we don't need to learn maximization question because we only need to learn the minimization question. You take a minus sign. Right, so any optimization question in any way, you can always make a minimization question. Okay? No matter what kind of optimization question, you can always make it mathematically minimization question. So we only teach minimization solution because that's the general case. You can always make that. Okay. And for example, we talk about least square approximation, right? Least square solution of minimization question. And then in the later part of the lecture, we talk about maximal likelihood. Okay, maximal likelihood, the solution for your statistical equations. So maximal likelihood, we're going to find that parameter maximize the likelihood, right? Okay, we didn't talk about likelihood yet. We have not talked about likelihood yet, but later in the later lecture, we are going to talk about likelihood concept, and then we're going to maximize the likelihood. But in a very simple linear regression, the solution of your beta or least square solution is exactly the same as maximal likelihood solution. They are basically the same. Okay, you can use a very completely different approach, but the solution is exactly the same. But in a more complicated case, the maximal likelihood solution is usually better than the least square solution. Okay, from statistical sense. So in later lecture, we talk about maximal likelihood. So you want to find your maximal likelihood, right? Which means that you want to find the minimize the minus maximal likelihood, right? So that in that case, you want to understand how to find a solution for your maximal likelihood. Is it okay? In later case, we'll come back to that point in the later lectures when we touch upon the likelihood concept and Bayesian approach. All right, so finally, I'm going to talk about some application, and the application is in fact your homework. Okay, so Belarotic is a biologist. He developed an equation for Zooplankton developmental time. Okay, developmental time. Developmental time means how many days that zooplankton is going to grow from one stage to another stage. Like insect, how many days it stay in egg, how many days in larvae, how many days in pupa, how many days in pupa eventually metamorphose into adult. So that's called development time. Okay, how many days it stay in that developmental stage? Okay, to go to the next stage. So Veronica find empirically it is very interesting. Still today we don't know why, but interestingly for like insect or zooplankton, whatever stage development, the developmental time follow this equation. Okay, developmental time can be several hours or several days, depending on this equation. Then depending on what? Depending on temperature. Of course, the temperature higher that the influence the developmental time. Okay, but A and alpha and B are some parameters. Some parameters you have to estimate. You do experiment, right? You culture that zooplankton at a different temperature, right? And then you see how many days they're going to develop to the next stage, right? And then you can fit and get to that parameters. All right. And also, from many empirical studies, the biological find B is usually minus 2.05. Okay, no biological explanation why minus 2.05. Okay, that's really energetic, but there's no mathematical, there's no theoretical explanation why usually this number. Not always, but usually this number. It's kind of still in the developmental biology, mathematics of developmental biology. Still no explanation why it should be this number. Okay, but this is empirically found. All right, so this is the data I took about this paper, so published in 1980s by Vidal. So he do this incubation experiment of this copepod species, and then he cultured the copepod in a different temperature, and that's the reason different stage. So in the usually in the higher temperature, the time is lower. Okay, so this is red dots are these are data. Or these are data. And then there are four. So let me show data. Data is ridiculously simple. Of course, just do experiment, it take a lot of time to experiment. But anyway, so he calculated the three temperature, and that's for different stage. Okay, C2, C3, C4, C5. That's just developmental stage, like insect different stage. The zooplankton have different stage. So for each stage, you have a corresponding temperature, and this stage corresponding time, developmental time. Okay, and this one. So like that.
Right, so this is the C1, C, and C2, C3, C4. Okay? And then as a red dots are the data I provided on NTU pool. Okay, the data is already there. Okay, so your homework is to find the blue line. Find the blue line. Okay, find the blue line for each C1, C2, independently, separately for each, or not together, or separately for each stage. So we're going to fit the biological equations. Okay, that's the second homework. Okay, so you are going to minimize the least square error, and then to simplify the question, you set b is minus 2.05, and you're going to to find a and b. Okay, for each C1, C2, C, right? For each stage, but separately, right? And then that's your answer. So I already provide an answer. Okay, so if your result do not look like that, you're wrong, right? So that's the answer. But of course, you have to write your own code. You cannot copy paste. It's your homework. You have to write your own code, and then you can make it exactly plot like that. Okay, exact. I'm saying seriously, exact. Okay, because you are going, that's a very simple question. So you should be able to find exact the same curve. Okay, exactly the same curve. Okay, for each. So that's your homework. Question 2. Okay, so you can use built-in function, right? You can write your code if you like. You can write the Newton function, or you can write the simplex if you want. But I allow you to use the built-in function. So in R, there's a optima. That's the function you can call to find the optimization solution for your equation. Again, keep in mind you need to minimize the least square. Okay, not to minimize that equation. Okay, minimize this square error. All right, and so that's your job to learn how to call this function. You can Google or you can have help how to call this function. Okay, if you use R, how to call this function. If you use MATLAB, how to call it, mean search in MATLAB. Right? So basically, you need to write your optimization function, what you want to optimize, and you call that. You call this function is going to refer your research question, and then put in the parameter and so on and so forth. Right? So that's your job to figure out how to you call this function. Right? It's simple enough, right? Because I don't even ask you to write a function. Right? So, but you need to learn how to call this function. Right? You have to set up some kind of function for your research question, and you use that, call your function, and then you're going to pass the parameter and so on and so forth, pass the data. Is okay? All right, now okay. If not okay, you can Google or you can type help Optima, and then you get the example how you should do that. Okay, you should be able to do that. For mean search also. So that's your question 2. The question 1, I do want you to write the equation. I do want you to write your code to do the Newton-Raphson method. Very simple, right? Newton-Raphson method, the iterative calculation. Then you write your own code to do the iterative calculation. In order to do that, of course, you need this is remind again for Newton-Raphson. For Newton-Raphson, you need f prime, right? You need to first calculate your f prime. Okay. And that question is simple enough. You can calculate the f prime. So that question is the sine over x. Okay, sine over x. So the problem, the f of x is this. Okay, f of x is this. And then you need to write your code to the Newton-Raphson solution for this. Again, you can set the tolerance like that. And be sure to try different initial value. Okay, in this code also, that we recommend to try different initial value and then to find a minimum. Okay, you can try a different initial. Randomly, it's okay to try randomly different initial condition. Okay, any question for homework? This one should be easy.
because you just all you need to do is write this simple code and then also learn how to use optimization solution. Okay. Okay, homework presentation for next week. Everyone has to do at least once, and if you do more, you get the extra bonus. Yeah. Another one. Do we have another presentation? If not, that's okay. We just one presentation. That's fine. Two. Okay. Two. All right. Good. So that's all I have for today. All right. And then you are free to go. And all you need, you like to do homework here, and TA will help you if you have a question on the previous homework or this homework. All right. And then I almost finished my job, but I will come back in almost to the end. I talk about neural network after you learn many more other things. I talk about finally the probably most challenging part is to write your code to simplest neural network. Right, I'll see you in the end of the semester.